Good afternoon. Today's lecture should really help you with the project. If you want to score high on the project, then on the hardware side, many things in this lecture will directly benefit you in that endeavor. So let's see what are the issues. High-level ideas were explained in L20, and I'll show you some more implementation stuff. And actually I forgot to load it, but I'm going to load some code also in the repository so that if you really want to see the real code for these things, that is possible. So first thing I want to do is show you how epochs are implemented. So epochs was a way of resolving control hazards. We just introduced a register called epoch, and very first thing we do is at the execute stage, anytime we detect a misprediction, we flip the epoch. We change the epoch to the next epoch, and every instruction that enters the execute stage, so fetch stage attaches this epoch to every instruction that is going forward. So if you want to think of it as a color, you know, all the instructions are red to start out with, and then you detect a misprediction, so now we go to a new color, say green, and after that all the instructions will be coming in green until there is another misprediction. And the important aspect of this is that once you have flipped the epoch, anything that comes from the old color is garbage. It's wrong path instruction and needs to be deleted. So the high-level idea is actually straightforward, and if you spend some time thinking about it, I think it should make sense what epochs do. And it's a very, very general solution because it doesn't depend upon how many cycles are being taken in different parts. It's really a question of tainting something and changing the taint only if necessary, only if some condition happens. All right, so in our two-stage pipeline, my first attempt is to just, because epoch code is very, very simple, let's assume there is an epoch register. So as I said, as I pass things forward, while enqueuing things in F to D, I'm also going to pass the epoch. So that's what you see here in red. There is another field in the record called epoch. Now, if you see the execute stage, as expected, I take out the epoch, right, from the incoming instruction, calling it epoch D here. And if epoch D happens to be different than what epoch I'm seeing currently, then this instruction is wrong path instruction. This instruction needs to be thrown away. And that's what it is. So you're checking that the epochs are the same, and then you have the right path instructions. Otherwise, you have the wrong path instructions in this. So not so difficult to write, and you know, when you get a misprediction here in the middle, as you see it, oops, sorry, what did I do? Oh, this is not the pointer. Where is it? I can't see it. Okay, so as you see, if there is a misprediction that the PC that you have computed is not the predicted PC that came in with the instruction, then you know there is a misprediction, and in case of misprediction, you're setting the PC and you're changing the epoch. Very small change to implement this idea of epoch. And now, oh yeah, there's one more small thing. I have to worry about this guard, because in multi-cycle processor, these rules are mutually exclusive. If you are in state fetch, you did this. If you're in state execute, do this. If you're in state something else, you do some other rule, etc. But now we are trying to execute fetch and execute together. Right? So the guards have to be relaxed. You are no longer, you know, we want fetch to happen every time. We want execute to happen every time. On the other hand, in the execute stage, there is still a possibility that you may issue a load, and then you'll have to wait for a load wait. You have to wait for the load to come back from the memory. And therefore, we have to know whether we are in the execute stage or we have entered load wait state. Right? Otherwise, execute goes to execute goes to execute all the time. Once in a while, it'll go from execute to load wait to execute. So that's the guard over there. Okay. So very happily I ran this, And what do you see? So there are two designs here. This is the 3-cycle or multi-cycle processor you had earlier, and this is my 2-stage pipeline attempt. And what I notice is that the clock period got worse. And you should pay attention to the column marked retiming, and I will explain in a second what that is about. Okay, so timing didn't change so much, but look at GCD. For what happened to GCD? Instead of taking fewer cycles, it's taking many more cycles. Oops, the goal was here pipelining, we're going to take fewer cycles, higher throughput. Things got worse, actually, so this is very problematic. We have failed, so even though you will get right answers by running this stuff, no error functionally, but as far as the goal of pipelining is concerned, we have totally failed in that goal. And so how come the cycle count for GCD not decrease? What happened here? That's what we need to understand. And if I just show you fractions of the code, fetch stage is writing in PC, right? And so is the execute stage. It doesn't write in PC all the time, but it writes it in case of misdirection. And what does it mean when you have two rules trying to write in the same location, when there is a possibility of both the rules trying to update the same register? We call it conflict. These rules conflict with each other, and you will not be able to execute them. They can't fire at the same time. This is a problem. And if they can't fire at the same time, you don't have pipelining. Not surprisingly, the number of cycles needed to execute this program went up as opposed to going down. Okay, so do fetch and do execute, conflict, can't execute concurrently. So let's try to understand a little bit more about this program. All right, so I look at this and let's see, what is the next question? Now the question is, even though the number of cycle count increased a tiny bit, let's just focus on this one, the one with control hazards, right? Why is it increasing? Why is the over multi-cycle stuff, why is it increasing? I mean, we didn't meet our goal of cutting down the cycles, but how can it get worse than multi-cycle? Any theories, any ideas as to what might be contributing to that? Think of it like this. In the multi-cycle case, you never have wrong PC. You take multiple steps to do an instruction, but whenever you go back to fetch, you always have the right PC. So there is no such thing in multi-cycle thing as doing a wrong path instruction, right? That possibility doesn't exist while it exists here, right? Because you may have fetched something which may have to be thrown away, etc., and that will contribute. Unnecessary wrong path instruction fetches. And if you do the calculation, you can figure it out. If there were so many branches here, every time you have a wrong path instruction, you're doing an extra instruction fetch, and that will contribute an extra cycle to this. All right? It's also surprising that it actually did slightly better in case when there were no hazards. I mean, this is nothing to write home about, but you still wonder, how can it go faster than multi-cycle? Right? So no hazard means that there is no data hazard, nothing, right? And similarly, in case of this data hazard benchmark is designed to have lots of data hazards. And in both these cases, you see that the execution improved by 4 cycles. That's problematic too, or not problematic, puzzling too, right? How can it reduce? I could give you the answer, but I thought it will be a good discussion tomorrow in the recitation, try to figure it out, how that could have happened. And I'll give you a clue without really giving you the answer. There is still a teeny bit of pipelining going on here. In spite of everything, right, there is still some pipelining going on, and you will have to figure out when that is happening. Okay, so clock period, and if you ignore the first column, no retiming, but only look at the retiming column, then you discover that there is no, not significant difference in clock period in this. So that's good news, actually. We expect no change in clock timing here. So now I have to tell you what retiming is. So this is something that compilers' tools do automatically at the back end. So suppose I gave you such a circuit, right? That you have F1, F2, F3, and there is a pipeline stage like this. Now, you know that you can move register in the middle here without changing the functionality. And the system indeed, the compiler will indeed try to determine if F1 plus F2 is smaller than, T2 plus T3. I mean, by moving this thing, let's see if it works. Fantastic. So if I move the pipeline stage there, it's slightly better. And this is called retiming the circuit. When you move the registers around a little bit in the data path to see if you can reduce the logic between them. And what we are seeing in these examples here, and repeatedly we are seeing it, you can get as much as up to 30% advantage in clock period. So on your project, you have to use retiming, otherwise you'll never meet the specified clock period. And Brian is very nervous because apparently computers are crashing when he turns on retiming, right?
It's work in progress.
Work in process, all right.
Should be fixed today.
So retiming you don't have to understand in detail right now, but all I'm telling you is that there is a flag in the compiler which has to be turned on in order to see how fast your clock can go. So this is a very, very standard thing that is used inside compilers. All right, so now let's look at some more stuff. So our basic problem was conflict between fetch and execute rules. How can I avoid the conflict? Easiest way is to introduce an EHR. So suppose I said both PC and epoch are going to be EHRs instead of ordinary registers. Now you can see what I'll do. So I have put this thing, marked it all in red over here. And I start out with the execute rule because that's the one that dominates, right? So anything that happens here should be visible to others. So I write down PC equals 0 gets, whatever it was going to get. And once I do that, then in the fetch rule, I must be reading PC1 if I want to see this value. I know this is going very fast, you can't see those ones appearing over there. So I'm setting it here, and I'm creating a bypass to the fetch stage. That's 1, right? And that's where you're reading the PC. But notice that we also assign to PC in this. Oh, no, there are quite a few reads. All the reads will be 1, right? This one. But this one, where I'm writing into PC, this is being written later, right? After I have the new PC, etc. So I'm writing PC plus 1 get PPC. And I do exactly the same thing with epochs. In the fetch rule, it will be all zeros, right? So I read it here. I read the old value of epoch, and whatever I'm writing here, I want to see it in the fetch stage. So this epoch, in this rule again, I'm reading it here, it's 0. But when I read it over there, I want to read the new value of epoch, whatever has been set by execute stage. Now the main reason for doing main reason for doing EHRs here is so that these rules won't conflict anymore. So there are no double writes in PC anymore, right? Because, you know, they are writing in different ports, and when they write in different ports, there is no problem. And when you do that, indeed, the results improve. What do you see now in the two-stage with EHRs? Timing went up from 611 to 947. Why? Why did the clock get worse?
We added more complicated logic by adding a bypass.
By adding bypass, we are elongating the combinational path between registers. So whatever was happening in the execute rule, now that logic is being added to whatever was going to happen in the fetch stage. And whenever that happens, you know, you will expect the combinational path to increase. And because now two rules are firing in concurrently, we expected the number of cycles to decrease. Boy, did they decrease, right? So now you have 2,222 cycles for GCD. Dramatic improvement. And that's exactly what we were looking for in this. We wanted to understand, you know, what can we do so that my program will take fewer cycles. So the message is slightly complex, because what we have to do here is EHR reduce the cycle count by eliminating the rule conflict, right? So that's the good news. But caution, but increase the clock period. So now, as a practical matter, you are always trying to judge, you know, the amount of loss in the clock period. Is it justified by the gains in performance? And this is the game that is played constantly when we design complex processors, right? We have lots and lots of ideas, right? How to reduce the cycle count, but we have to constantly pay attention to, did I make it so complex that now my clock period will get worse? So this is a very simple but clear illustration of that principle, right? So the message is, exploiting rule concurrency in the common case is essential. If you don't exploit concurrency, you really don't have pipelining. I mean, the only reason for jumping through all the hoops here is to make these two stages go in parallel, to execute them concurrently. And if that's not happening, you don't have a pipeline machine. But the caution is, since EHRs can make things worse, you know, use it carefully, do some performance measurements to see, are you winning or not winning in this? Okay. Now, the question is, if I look at this and I see, my gosh, the clock time increased from 611 to 647, is there any other trick I can play which will not increase the clock time so much? So think at very high level what's happening here. In the execute stage, you were decoding, you were executing the instruction, and then you were signaling something, right? It's not surprising that this is a lot of things going on which is being added over there. Maybe I can do the following. Instead of jumping from here to there, I delay my jump by one cycle. I remember I'm supposed to jump, but I don't jump. If I don't jump from this rule, then this rule won't conflict, because the conflict came about because both rules were trying to update the PC. So I will have a new state. I'll say misprediction, right? And I'll have a new rule. I'll jump to that rule in case of a misprediction, and then play the same game with EHRs. So that rule has very little logic, and it may not make the clock worse. It will take an extra cycle in case of a jump. And that's exactly what we did here in this delaying the jump. This is a very, very common trick, that whenever we have something not so common, because we expect the common case to be, there is no misprediction. So if there is a misprediction, we say, if you take a little bit extra time in that case, maybe it'll be okay. We have to test this hypothesis, but that's the design idea, and let's do that. So what I did here is, I'm going to move this code, which was updating it, right? I'm going to move it from here to over here, I have introduced a new rule called redirect. And of course, I'll set the state to be redirect and so on. So does everybody understand what happened here? Even in case of misprediction, execute and fetch can go on in parallel, because that's not setting the PC anymore. And I have delayed the jumping to new PC by one cycle. I'm going to another rule, called redirect. And if I do that, my hope is I'm losing in some sense, because in case of misprediction now, I'm going to introduce an extra cycle. So why am I doing this? Because I want to see if my clock period improves. If I've reduced the logic, in the execute rule, if I've reduced the logic in the bypass path, does it actually show up or not? And let's just see it. Before I show you the results, I have to point out a few more things about this code, right? Okay. So I have now changed it. Here you can see that state is redirect and next PC is, this is a new register. I'm assigning this thing. I will jump over here and PC 0 gets next PC, epoch gets blah, 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 and state gets execute. Not so difficult. The only problem is we have to remember the next PC into some registers here, which is what we did. Okay, good. This is the thing you better get used to. Anytime you have an idea in architecture and you say, okay, I'm going to do it, and then you will see the machine broke down. It just doesn't execute correctly. Say, what happened? This seems so straightforward. I moved code. And this is why hardware design can be very difficult. And actually, once you start facing problems like this, then a language like BlueSpec with its atomic actions, etc., will really pay you huge dividends. What's happening here is, do redirect. You see, you have delayed it by one cycle, right? Is the fetch sitting idle during this time? What is fetch doing? It's merrily going, right? Because we designed it so that fetch execute can execute in parallel. So you say, okay, execute goes there for the redirection stage. In the meantime, fetch has fetched another instruction. Wrong path instruction, but it has fetched. Very busy, it's doing something. And what you will have to do in the redirect stage now is throw away that instruction. If you don't throw away that instruction, it will block everything. The damn thing will come and sit in the queue so what you have to do is you have to introduce more code here, which will say that that instruction that is sitting in F to D, please delete it, right? So dequeue it. And the instruction that is coming out of the memory, you write it in inst, but it will never be used. It will be just thrown away. It's a local variable. So this is the wrong path instruction that got fetched and it's going to be thrown away. Is this high-level idea clear to everyone? That by delaying the branch, I don't know still whether I'm winning or not, but we'll see in a second. But the complication is now some more activity happened on the wrong path, and that all has to be taken care of. And what do you see? What happened to the critical path? What's the clock period like in this new design? We are back to 599. It made a dramatic difference, right, in the clock period. It went from 947 to 599, which is very, very good news. I mean, basically by delaying it one cycle. And where are you paying the price for this? Look at the next column. The number of cycles went up for GCD, from 2000 to 2700. You can do some math. You can multiply these numbers and see whether you are winning or not. Because ultimately what you want to know is number of cycles times the clock period. And you will discover you actually win by doing this, right? So delaying redirection, improve the clock period, but increase the number of cycles as expected. So what is the best execution time for GCD? So I just plotted it here. Indeed, the last one is the best. So now I'm just multiplying the two things, you know. What is the clock speed and how many cycles it took? And we started out with 2081 in our multi-cycle machine, and we end up with 1625. 20% gain in the performance over multi-cycle thing. And that's why in architecture, there is continuous tuning that goes on when you design machines, right? You may have a very wide plate of tricks you can play in the design, but you don't know which one will work for you, right? So you have to keep trying. You have to keep trying and seeing, you know, what is giving you the good performance. And of course, I am shortchanging you a little bit by showing you just GCD. You will have to do this study on huge benchmarks. You will have a whole store of programs which are very important for your customers, and you run them and say, you know, in almost all programs, you know, my new hack works. And by the time you become as important as Intel, if you bring out a new processor, even on a single benchmark, if it does poorly than the old one, there'll be complaints. I mean, the network will get flooded with complaints, internet will get flooded with comments, you know, there's new stuff, you know, that old program runs 3% slower. So people are very happy with all the gains, but they're not willing to concede even a little bit. So it's a very tall order, you know, when you improve machines, that you really, general purpose computers, they have to improve all across the board in order for them to have the right marketing pitch, etc. for this. And you're getting a glimpse of it here. And just by one program, you know, really, you'll have to run lots and lots of programs. Just to give you an idea of how much computing resources go towards evaluation of all this stuff, if you went to any company that is manufacturing computers or processors, you will have building full of computers doing nothing but simulation. Nothing but running benchmarks after benchmarks before the machine is produced in the design phase. So it's a very, very compute intensive activity. You know, you just run them constantly, right, to see how various programs are doing on my new design. Okay, but we are happy, right, because we had some architectural idea, it seems to have worked out. Very good. So now let me go to a three-level pipeline. And what I did here is, I think when I go to 3 stages, because I'm essentially trying to split the execute stage, where right now we used to just go to load weight. But in the execute stage, I was doing decode and execution of the instruction. So suppose I break it. I say 2 stages or 2 cycles. Let me just be very simple-minded first. So in one cycle, I'm going to decode, then I'm going to execute, and then I will have load weight if I have to. So if you think of the machine like that, you know, my simple machine, I'm calling it 4 cycle, where I have separated this thing. What do you expect when you go to a 4 cycle machine? So you have fetch, decode, execute, and load weight. What do you expect? Do you expect any gains even in multi-cycle case? See, I think we have some evidence that the execute stage was the one that had the longest data paths in it. That critical clock was being determined by that. So by splitting into 2, it's conceivable that your clock will go faster even in your multi-cycle machine. And indeed, when you compare the clock for 4-cycle machine against the 3-cycle machine, what do you see? The clock went down from 593 to, it went down from 593 to 454. That's a huge improvement in clock, right? Huge improvement. So yes, of course, the number of cycles to do the program went up from 3,500 to 5,000, but you also gained quite a bit in the clock speed. So that suggests to you that if our goal is to have very fast clock, we really have to split this stage. Now, if you're going to split the stage, then it also makes sense to ask the question, can I pipeline it? Can I do decode and execute in parallel? And that's what in your project you will have to do that, because unless you do that, you're unlikely to meet the timing specified in that project. And when you do this three-stage pipeline with bypasses, I'm not going to show you the code for this. For the other stuff, I'll post all the code, but this one I'll give you some hint as to what happens in this code. All right, so let's see what is the bypass code that you get over here. So I'm not going to touch the fetch rule, so I'll leave it alone. Now look at the decode rule. Very simple. I do the decoding and I pass the information to execute stage, the decoded instruction. And then in the execute rule, I have the decoded instruction, I have all the values from the registers, and now execute it, and after that I'll have the load wait instruction. So this fat rule has been split into two parts. And what is the danger in this? As we discussed in the previous lecture, I think in L20 we discussed that this will immediately introduce data hazards. There is a danger that the values you read in the fetch stage, in the decode stage, are stale, because there may be instruction ahead of you which is trying to modify those locations in the register file. So you have to be careful about that. And the solution was to introduce a scoreboard in this. And when you look at that picture, it looks something like this. So you have a scoreboard which keeps track of who's ahead of me. And before I can enter the execution pipeline, I'm asking, because I'm going to be reading these registers, I'm asking, is there anybody ahead of me which is writing in these registers? If that is the case, then I'm going to stall. And I'll stall, and these things will drain out, slowly, and then I will move also. So that's the whole idea behind resolving data hazards in this. And I think we're going to give you the scoreboard design, even though it's very simple, but that will be given to you. When an instruction is removed from the scoreboard, its update to the register file must be visible to the subsequent registers in decode. You see, this is something now I can assert because of atomic rules. So we have to make sure any time I write in register file, right, I can remove instructions from the scoreboard. But if I ever removed an instruction from the scoreboard without writing the values in register file, hell will break loose, right? It'll be just wrong. You'll get wrong results. So these two actions, removing from the scoreboard and writing into the register files, have to be done together. Similarly, at the dispatch time, I have to ask the question, is somebody else writing ahead of me? And at the same time, I go and read the value. So the assumption is, whosoever left, its effects are visible in the register file. Otherwise, register file will be stale. So this is now becomes something high level, becomes our invariant in the design. We have to make sure these properties are preserved, and for that, atomic actions are fantastic, because you will make sure that remove from scoreboard and writing register file is done in one rule, search and reading the register file is done in one atomic action. So if you keep these things like that, the certain level of correctness is guaranteed here. So to detect hazards, you have to have the source fields also specified as baby, because otherwise you don't have a real hazard. So I think we have modified that decode code for you. I'm calling it decode 2, but I think in the repository it's just probably called decode. All right, so now let's see what's happening. So you decode the instruction, and the red line shown here is where hazard is being checked. Can you read that headline? What is it telling you, that line? In scoreboard, you're searching, and what are you searching for? if there is a destination corresponding to the source in this instruction, source 1. Similarly, you have to do a search for source 2, right? And if any of either source is being modified ahead of you, this instruction can't go, because then it'll end up reading stale value. So that's this check being performed. All right, so if this is happening, then you are on the right path, because there was no, this is the not opposite of that written here. So you are on the right path, there is no hazard here. You can go and execute the instruction as is, and whenever you execute the instruction as is, the new thing you are doing is now you have to insert this instruction in the scoreboard. Because now this instruction is going to be in the execute phase, and the things coming behind it must check whether its destination affects them or not. So that's what you're seeing here, that scoreboard.insert has to be in this, and after that again it's straightforward. So this has even a more subtle bug, and it has such a subtle bug that it made my head hurt first time when I made this mistake. So tell me what's happening when when you detect a hazard. What's happening to this instruction? So I have fetched an instruction and I detect it's a hazard, so I have to wait. In the next cycle, what do? I test this instruction again, right? Not a new instruction, I have to check this instruction. I cannot throw it away, right? Otherwise, you are throwing away a good instruction at that point. And when you see it like that, we need to keep the fetched instruction while stalling. We can't afford to throw it away because it hasn't been executed yet. And if you don't take some extraordinary action, if you look at this code, we'll happily get another instruction from the memory. We'll happily get something else from F to DQ, right, at that point, and this instruction is gone. Not right. So now I have to introduce another register where I'll hang on to this instruction, need a register to hold the fetched instruction while stalling. Okay, so I can't DQ it, right? Because this DQing should only be done when the instruction has been dispatched. If the instruction hasn't been dispatched, so this DQing has to be moved here, somewhere else, right? Because if you dispatched it right there, that means you're throwing away the instruction. The stalled instruction must be saved. All right, so this is what no new instruction should be fetched in the stalled thing. So this instruction thing also has to be prevented, from fetching more instructions. You shouldn't look at the next one until you are done with this thing. So you will have to make some changes over there as well. So if you look at this code in the do execute part, filter wrong path instruction, execute like before, detect, etc., etc. But now you have to insert SB remove. Whenever you write in the register file, atomicity tells you that you must have sb.remove also right at that point. So you will have to insert that. Okay, so I'm deliberately not showing you the code because that's what you'll be doing on your project. Do people understand this at a high level? Do you have questions as to how this idea is working? I hope most of you can see how we detect hazards. And that was the easy part because we built this data structure called scoreboard. And I look at my sources after decode, I compare against all the destinations inside it. If there is no hazard, everything is fine. But in case of hazards, careful. In case of hazard, you are going to hang on to this instruction. You can't dispatch it yet because you're waiting for the pipeline to clear. What does it mean that I hang on to this instruction? I have to provide another register to hold it from this cycle to the next cycle. As long as I have to hold it, whatever time it takes to clear out this thing. And that will put back pressure, on the fetch stage, if it was sending me too many instructions, I hold it, I'm busy. Because I will not take off anything from F to DQ. I will not take off anything from the memory at that point. Because I have taken off this instruction which I haven't been able to execute yet. Right? So that's the idea, and that's the complication that you have to sort out in programming. And if you don't sort it out correctly, you'll get wrong results. I want to tell you about one more trick which is quite useful in your project. Until now, we have been using the simplest branch predictor there is, and that is I expect the next instruction to be PC plus 4. Because most instructions are not jumps. And if they're not jumps, then PC plus 4 is a very good prediction. But since every time we get a prediction, misprediction, we lose something. We lose a cycle here, lose a cycle over there. So it's a well-known fact that if you improve your branch predictor so that its predictions are more accurate, so suppose your accuracy was at 70%, if you played some trick and made the accuracy 85%, you will see immediate benefits in cycle counts. So what I'm going to show you is the most essential branch predictor. There are many, many schemes out there, but this one is simple, and every machine has this predictor. And the way we think about branch predictor is it's learning from past behavior. Now, why is that a good idea? Suppose you have a program, right, and you have a jump instruction in here, branch instruction here. If it goes to that point, we bet on the fact next time when you execute this branch instruction, it'll again go there. So past, the way it resolved in past is usually a good predictor for future. There is a much higher probability, and it comes primarily from loops. So if you have a loop, you come here and you jump back, you come here and you jump back, right? So, and it's certainly true for jumps. If it was a jump instruction, you know where to jump to. There is no reason for paying a misprediction in that case, except the first time. So if I could memorize somehow, if I could remember that for this PC, this is the prediction, this is the better prediction than PC plus 4, we are in, it's worth trying. My normal prediction is after PC I execute PC plus 4. But every time I take a branch, I actually remember the target where I went to, and I remember these pairs. This PC, the target is this. For this PC, the target is this. And I store these pairs in a data structure called BTB, branch target buffer. Oh, so I'm getting way ahead of me. All right, so this is your branch target buffer in this. And once you have seen caches, everything looks like a cache. This is a cache too, right? So just as TLBs were a cache, right? Translation look-aside buffer for remembering the most popular translations. Now we are trying to memorize, that these branches resolve that way. And we only put something in BTB if it jumped. If the next instruction was PC plus 4, we never enter it in BTB. We only enter it if after this instruction you went somewhere else, so we remember that thing. And that's the pairing you are seeing here in this thing. It's called entry PC. Entry PC is the PC that you had looked at, and target PC is the place where you jump to. Now the funny thing about this structure is, first of all, how does it function? I want to keep it very simple because this is extremely tight loop. I have to do it within a cycle, right? Because I need the next PC immediately. PC plus 4, was the right thing because it was very, very fast. So in this one, if I can do a little bit better than PC plus 4 without increasing the clock cycle, etc., I'm doing very well. So what I'm going to do is, I suppose have 4 instructions in my 4 entries in my BTB. So I look at the lowest 2 bits of my PC, and it's a direct map thing, so I'm saying where is it? And then I go and enter the PCs corresponding to it if it jumped to something other than PC plus 4. If I don't find it in my table, then I say next prediction is PC plus 4. So just by this much you can guess that in the execute stage, when I actually know where this PC goes, I have to go and make that entry into this data structure. So in the fetch stage, I'm just reading it. I'm reading it. I'm seeing what is the next prediction. And execute stage corrects the predictions. And this machinery is extremely forgiving because after all, it's just a prediction. If the prediction turns out to be wrong, you already have implemented the machinery to automatically correct it. So there is no burden here. You can put any garbage you want in this. It should not make your machine incorrect. It can only make your machine slower because you will be getting even more branch predictions than you should have with PC plus 4 predictor. So what history has shown is that even small BTBs are extraordinarily effective. They dramatically improve the performance of your machine. And you really cannot have a huge BTB because otherwise it will slow down the clock. You have to compute this very, very fast. Quickly you have to determine the next PC. And you can have as much inaccuracy in it as you want. This is just showing you that this BTB structure is in a very tight loop, right? You read something, consult the BTB, and you immediately say, this is the next PC that should go in there, right? So this is the tight loop. Timing is crucial here. But this thing, at the execute stage, I go and find the correct prediction. I go and do it. I can do it at my leisure. If I am unlucky enough to go to that branch several times even before I get there, okay, I'll get another misprediction, but sky is not going to fall because of that. So we can afford to update it slightly in a delayed fashion, but we cannot afford to take any time in referring to what is in BTB. All right, so BTB implementation details, you can figure it out. I won't spend time on this. People play so many games. They say, I don't want to waste too many bits on this. So instead of having the whole entry PC, they will have just a fraction of PC in there, right? They don't even worry about valid bit. Who gives a damn? If it's not valid, you'll pick up some other garbage, from the BTB table. So they save every bit in this and try to do it as as small a structure as you can. And there is overwhelming evidence that BTBs improve performance. So this is a simple enough idea. I really do expect at least some of you will implement it in your project and see how much more you get out of doing this. Okay. Even small BTBs are very effective, that is the thing. And this is the interface in BlueSpec for it. You only perform 2 operations on it. One operation is prediction. You give it a PC, it tells you the next PC. If it finds it in the table, it gives you the target. If it doesn't find it in the table, it gives you PC plus 4. So that's one thing it always does. And the second thing is update. You give it the PC and the target PC, and it'll just go and update the thing, and you're marking it taken. That I'm saying because later on we can use it for other purposes as well. All right. Performance of your project. What I want to show you here is just a couple of more ideas. This is going way beyond the course now. In modern processors, you have 3 different predictors. So you have BTBs, which are immediate. Then you have branch predictions, which are often called direction predictions. If you can go left or right, then it's trying to predict which way you're going to go. Then it also has predictions for stacks, right? So if you have procedure called stack, it's used in a very specific discipline, last in, first out. So we make all such entries in yet another table, right? And we use it for predicting, where we are going, when we are jumping somewhere, and when we come back, from it. And because of these advances in branch prediction, often in popular benchmarks, people can hit as much as 99.9% accuracy in branch prediction. For fast processors, branch prediction accuracy has to be very, very high, otherwise it will not be justified because the penalty gets higher and higher of misprediction. So by having good branch predictions, you can really do wonderful job over here. I wanted to show you, this slide is also important just to tell you we have only scratched the surface of what we can do to make our processors go faster. So what you saw here is pipelining, but if I want to run my pipeline at gigahertz, 4 gigahertz, it has to be much deeper pipeline than 4 stages. Typically it will be 10, 12 stages of pipelining, even in order execution, right? So you're breaking down things in very, very fine grain to get the clock faster and faster in this. And deeper the pipeline, more burden you have in bypassing. Because then if something gets resolved here and you have to bring it back, you're going to lose lots of cycles, right? So deeper pipeline are synonymous with, in terms of performance, by requiring more and more bypasses, and bypasses take a lot of area, in your system, also take a lot of energy. Okay, the other idea which is very commonplace, any processor you're using today, I think this is beginning to happen now even in embedded processors, we always try to execute more than one instruction at a time. So I fetch one instruction, I also fetch another one, so double the bandwidth of instruction fetch. And I try to do both of them. I try to do both the instructions simultaneously. One may be an add, one may be going to the memory, right? So by playing those kinds of tricks, I can gain significant performance without adding too much hardware. I can also execute instructions out of order, right? So if you play all these tricks, you will get a lot. Now, another thing you have to keep in mind, you're a designer, and if you just improved your processor and didn't do anything to the memory system, you will see no advantage. Faster your processor, hungrier it gets. It needs to get much more data out of memory, right? So commensurate improvements have to be made in the memory system to keep the system balanced. So both these things are very, very important and have their own complexity and fascinating topic of study. You can take several other courses like 6823, where you will learn many more tricks about architectures, and I may teach 6375 next term, which will be actual design of faster machines and accelerators, in that. Okay, so good luck with your project, and I hope you enjoy it.